Hey AP2. So today you're viewing this and it's going to be Tuesday, 3/17, or that's when I'm intending for you to review it. So we're working in our unit fluids here, and we really don't know what's going to happen with our test date. So we'll come to that later. I believe that we're not going to be working on our scheduled calendar anymore. I'll keep you up to date. So additionally, the long-term homework for this unit, long-term homework, is a no-go. Don't do it because you're going to be doing a lot of work inside this packet at home anyway. So skip your long-term homework. Google classroom quizzes. Yes, do those. Summary. Yes, do that. Then I'm going to be posting some labs and you're going to do those. So I'll be here for questions if you want to email me, and I'll find out about audio call when I can. All right, here we go. So first we got to know what a fluid is. A fluid, by definition, is a substance that can flow from one location to another and will take the shape of the container rather than the shape of their own. The term fluids also refers to liquids and gases. An ideal fluid is the ones we're going to deal with. It's going to be incompressible so that the density doesn't change. Then we're going to flow at a steady rate. So we won't have to worry about any viscous interactions with themselves. That's again the next one, to be non-viscous, no friction between the fluid and the container. And then no flowing back on itself, nothing that comes around like this. So we're not dealing with any sort of river twirls. So flows linearly. The main definition of fluid and how to pick one fluid and separate it from another fluid, one of those key properties is the fluid's density. Density is this symbol rho here. I guess I usually tilt mine in, even though in the typeset they tilt it out. Okay, so rho. So rho is defined as the mass per unit volume. Units of density are kilograms for mass per meter cubed. Of course, there can be different densities. You can have mass densities in different units of volume, but these are the ones we're going to be using our standard units for density. You can also have different densities like surface density or line density. We're always going to be dealing with 3 dimensions, so a volume density. Let's try this first problem. You can pause, read the problem, and then come back. So pause, try 1. Okay, I assume you paused and gave it a shot. So determine the mass of the air enclosed within a refrigerator. So you're going to have your refrigerator here. And it says that it is 0.6 meters and 0.75 meters and 1.5 meters. So we can find the volume. The volume will be 1.5 times 0.6 times 0.75. And then the density of air can be found over here in our chart. Feel free to use this chart throughout the entire unit. You're going to need it. So 1.29 kilograms per cubic meter. We can set that equal to the mass over the volume. Solving for the mass, we get 0.87 kilograms. Now it says to compare the mass to that of a dozen eggs, which have 44 grams each. So in our container of 1 dozen eggs, each one has a mass of 0.044 kilograms. So the total dozen, mass of a dozen, is 0.52. Now when you think about that, that's kind of amazing that the air in your fridge weighs more than the eggs that you put in your fridge. And it would seem like, how did the eggs not get squished by this? Right? And that's all a density concept. The fact that the air is all around you. Right? The air in the refrigerator is above and below and to the right and to the left of the eggs. So it's really not experiencing a crushing weight on top of the eggs. All right, follow up. What's the air in this classroom? Air can get heavy quick once you start thinking that it matters. Okay, so rho is mass over volume. So here we're going to say the density of air is 1.29 kilograms per cubic meter. And then we want to know the mass, m, and our volume is 9 times 14 times 3. We solve for our mass, and it's, oh, wow, 487.62 kilograms. Let's just compare that to the mass, say, of me. I'm 57 kilograms. So in my classroom, right, it's crazy that I don't get like squished by the air and crushed. But again, that's the idea of density, is that despite the large amount of mass of air, it's all around us, a low density. And so it's not going to apply this crushing force upon us. So let's relate pressure to force, since we're thinking about a lot of this crushing aspect. I normally take a moment to think about pressure and if it's a vector or a scalar. So force, is that a vector or a scalar? Force has a direction, so force must be a vector. Now, in order for pressure to be a vector, then area would have to be a scalar. So can area be a vector? That's the question. And the answer is yes. If you remember from magnetism, right, we have an area vector perpendicular to the area with the value of the area. So area itself is a vector. We divide out the vector property, making P a scalar. Pressure does not have direction. Pretty cool, huh? So pressure is force over area. It is a scalar. It has units of newtons per meter squared. But we call newtons per meter squared pascals. The symbol PA. So just to be aware, newtons per meter squared is a pascal. Let's try problem 3. Determine the pressure exerted on the skin of the balloon if a 2.1 Newton force is applied by a finger. Then you're going to apply the same 2.1 Newton force with a pin. Pause now. Okie dokie. Here we go. So we can take pressure is force over area. Take our force, 2.1, divide by the area. 1 times 10 to the negative fourth. So our pressure comes out to be 21,000 pascals, or newtons per meter. In this second scenario, we get a much larger pressure due to the smaller area. And that will pop the balloon. Balloons can withstand a pressure of 3 times 10 to the 5th newtons per meter squared. And by poking with a pin, we apply a pressure of 8.4. Let's look at the balloon pressure for a second here. Inside the balloon, right, there is air. The air is pushing on the skin of the balloon to extend it outward. And then the air from the outside is also pushing on the balloon, like this here. And so this skin of the balloon is just separating this inner air pressure from the outer air pressure. But the pressures are the same. That's why the balloon is not expanding or contracting. So you might realize it's hard to initially blow the air into the balloon, right? And that's because you need to expand the pressure inside the balloon, actually making the air pressure in there bigger to push it with a larger force on the skin of the balloon. But now that we're in equilibrium, those two pressures are equal. Okie dokie. So let's go on to atmospheric pressure. Here it says we're essentially all living at the bottom of an ocean of air. In earlier calculations, air has a significant weight. And so if we just consider a column of air, 1 square inch, how big is that? Let's see, kind of like this, an inch, 1 square inch. Stretching from the sea level to the upper reaches of the atmosphere. So take this column that you just drew, extend it all the way up. Whoosh, whoosh. Keep on going to the edge of the atmosphere. So you have a very, very long column. This column will weigh 14.7 pounds. So pressure from our atmosphere is 14.7 pounds for every single square inch. We're going to use that number, but in standard units. So atmospheric pressure, which exists basically always, is going to be 1.01 times 10 to the fifth Newton per meter squared. Get ready to see it in kilopascals. So atmospheric pressure is 101 kilopascals. Sometimes simplified as just 100 kilopascals. Sometimes, and on your formula sheet, you'll see they leave out this one right here. Okie dokie. So we're going to try these next two problems. I'm going to let you read them and think about them. And then I'll come back and I'll do them with you. Okay, so let's look at the idea of pressure here. So if we have this atmospheric pressure, that means we have you with this giant like cone of atmosphere on top of your head, right? And where does that pressure come from? Right? That pressure is a force, which is the weight of the air. So this air has a density of 1.29 kilograms per cubic meter. And then if we take this area that's on top of your head, and then we multiply by the height of this column all the way up to the atmosphere, we can get a volume, right? Height and area. And then that volume that we find, along with the density of air, can give us a mass of air. And then you know that mass times gravity gives us a force. And so this pressure on top of our head comes from the weight of the air on top of our head. Now, if we actually did that calculation that I just described on the right, you're not going to get the proper atmospheric pressure, 14.7 pounds per square inch, because at higher altitudes, the column of air above you is shorter, right, and lower density. So as you go on top of a mountain, there's less air above you. But the sneaky part is that it's lower density. So that 1.29 that we're talking about is not going to be used for this whole height here. It's going to be more an integration problem. So just as an example, on top of Mount Everest, the atmospheric pressure is only 4.37 pounds per square inch. That's drastically different than the 14. So our air density changes dramatically, which is also part of the reason why you have different boiling temperatures and such, right? We'll connect that later. Okay, so let's use this concept of pressure to think about what's going on with our hand here. So it says, let's use the fact that we have this column of air on top of our hand, right? This column, we know, has some mass and then times gravity and has some downward force. So this air is pushing down on us. And if we want to figure out what that is, we can just take the pressure, 14.7. Oh, or we can do it in metric units, I guess, because our area is given in metric units. So let's back up real quick. Okay, 1.01 times 10 to the fifth newtons per meter squared equals our force over our area, 0.008. And the force exerted on my hand is 808 newtons. Whoa. In pounds, just doing this quick conversion, that's 181.56 pounds pushing down on my hand. What the heck, right? Why don't I feel that? Well, what's going on is that below my hand, there's also a pressure. So if I examine what's happening, let's see, down here, make it a little darker blue. Right? Below my hand, there's also a pressure. So if we compare the pressure above my hand and below my hand, they're very, very close to the same, right? Because we just consider the atmosphere to be this one single number. But that's actually not true, because in this darker blue area, there's not much, a little bit, just this little section right there, a little bit more mass of air on top of this lower section of your hand. So the pressure on the bottom of your hand is actually bigger than the pressure at the top of your hand, creating a larger upward force than we have a downward force. So we have this downward push from the air here, but the pressure below your hand is actually a little bit bigger due to this extra weight of air. So the pressure on the bottom of your hand is just a smidge, teeny smidge more, because think about the mass of that air, right? Even times G is real small. So this pressure is just, this purple pressure is just a little bit more than this blue pressure here. And so in the end, it's basically like we feel a net force of 0, because we have this upward force and downward force that are basically the same number when we're in air. When we are in water, though, you feel that pressure difference between this purple arrow and this blue arrow is much more significant if this were water, because then the mass difference right here, this little baby mg that pushes more on this bottom part of your hand, actually has some significant weight, because the density of water is like 1,000 instead of 1, like air. And so that's where we introduce the idea of a buoyant force, buoyancy, when we're in water. We ignore that in air. So we really don't talk about the pressure of air being different. We just keep it at one constant number, although the pressure of air is different, as stated here, right? Depending on where you are. It's just such a minor number compared to water. Constantly considering the pressure from air is a bit annoying, right? To just have this baseline measurement of 100,000 pascals that you need to put in every time. So because of that, we refer to the gauge pressure. Gauge pressure is what a pressure gauge reads when you inflate a soccer ball or a tire in your car. So for example, if you inflate a soccer ball to 10 pounds per square inch, the pump is going to display a gauge pressure, P subscript G. So the pump actually says that it's 10 beyond the atmosphere, right? The pressure inside the ball is actually 10 above the atmosphere around it, so that the ball has more pressure than what's around it and can feel kind of solid in your hand, right? It feels like more force. So the gauge pressure is the amount above atmospheric pressure. So that's what our gauge will read, 10. What's really the pressure inside of our ball? So if the gauge pressure is 10 pounds per inch squared, the actual pressure inside of our ball will be that plus, let's see, minus P atmosphere, which is 101 kilopascals. Ooh, let's do it in the same units. 14.7 pounds per square inch. And then we solve for P. The pressure inside our ball is actually 24.7 pounds per square inch. Nice. Okay, on to our next one. Okay, so before you begin looking at section 2, static equilibrium, you'll find that on Google Classroom, I have posted a Google form, or like what you know as a quiz. And it's got a link to a PhET simulation. So there's a video on the overview of the PhET, and then there's these questions about the different pressure at different locations. So try out that first. So before you begin, before you start this page, before this page, go on to Google Classroom and do the simulation exploration. Please and thank you. Okay, so I'm assuming that you're coming back after doing that exploration, and let me do some deriving for you. I know it sounds like diving, but we're not diving, we're deriving. So what we're going to do is we're going to think about just the pressure inside of water, where the density of water is going to remain the same But since water is so heavy, unlike air, the different columns of water on top of us is really going to make a difference. So you know when you're swimming that the pressure down here on your little ears feels different than the pressure here on your little ears, right? And sometimes you feel like that popping and you feel bad down there. So let's explore what that pressure is and how you find it and how you can calculate it. So right now we have the top of this container. That's what I'm referring to as F top. And the air that's above the container pushes down on the top of the container, just like we did with the hand example, right? You know that there's a force on the top of the container, and that's just from the pressure of air being force over area. What's area are we talking about? The area that we're referring to is this area of our liquid here, right? Same as on the top and on the bottom, not that matters. Cool. And so rearranging this equation, we come up with the force on the top of the water is the pressure of the atmosphere times the area. Now let's look at the bottom of the container. At the bottom of the container here, we're not only supporting this force, but we also have this weight of water on top of us. So let's go ahead and think about this weight of water. Weight is written as mg. How do you find the weight of water? We'll go back to our density table in the beginning. So we got our density of water times volume. So instead of this m, we're going to write density times volume. Cool. What is the volume that we're talking about? Well, we have this area down here, this area, and we have the depth, symbol H, called depth. That's a weird word, depth, right? So then the next thing that we're going to do is we're going to replace this concept of the volume, let's pick a different color, volume, with height times area. Sorry, that's my dog. I'm sure you can hear her. Okie dokie. So let's set it all together. So the force on the bottom is the weight of the water, right? That's what this is, weight of water, plus the force on the top. And then what you can do is you can take all of this expression and you can divide by area. So force divided by area, force divided by area, weight of water, which is a force, divided by area. And then a force divided by area becomes a pressure. So we can define the pressure at the bottom to be equal to the pressure at the top plus rho GH, because the areas cancel out. And so that's really cool. What that says is that at any specific depth, that's what that H is. Not height off the ground, but depth below the surface. So surface, and then down below, that's H. It's not from the ground. It's measured from the surface, right? It's the amount of water below, the depth, how far below you are. And so the only thing that determines the pressure is the density of the fluid and that height that you're at. And of course, what's on top of you. So P bottom is P top plus rho GH. So P bottom is P top plus rho GH. H being depth. Nice. So let's try and do these two. Stop and test them out before me. I'll draw them for you. So pause anytime you're ready to just start by yourself. I'm just drawing a nice backyard swimming pool. 1 meter, 1.5 meters, 1.5 meters. I'm just guessing, what a swimming pool is. I don't own one, so feel free to set up your own dimensions if you own a pool. I'm going to come over and swim in your pool, perhaps, once it's warm and we can see each other again. Ay, ay, ay. There you go. Some water in the pool. That's good. All right. So let's check out the pressure at the bottom. Remember, try it without me first if you want, now that you have your nice swimming dimensions. P bottom equals P top plus rho GH. Watch out for your rho's and your P's. They get confusing. So P at the bottom of your swimming pool is the P of the atmosphere. That's what's on top. If you have a swimming pool in space, you got some serious issues. Beyond, there's no P top. So take your atmospheric pressure, 1.01 times 10 to the fifth. Notice your formula sheet drops the 1 newtons per meter squared. Plus the density of water. Where are you going to find the density of water? Ooh, that's a great question. There's this density chart in the front. Use it. Density, fresh water. 1,000. Unless you have a seawater swimming pool. Oh, what? Just kidding. Okie dokie. So plus rho G, and how far below the surface we are. If we're at the bottom of my pool with my dimensions, we're at a depth of 1. And so the pressure, the P bottom at the swimming pool is 110800. Now, that's pretty cool because you could be in the ocean, and if you were, that's the sand, if you were 1 meter down in ocean water, I was going to say you'd experience the same pressure in ocean water. 1 meter down. But ocean water is actually more dense. My point, though, was going to be that in maybe a giant freshwater lake, freshwater, then you were 1 meter down, the equation is still the same. It doesn't matter, lake, pool, baby pool, bathtub, 5-gallon bucket, 1 meter down, same exact pressure. So let's check this here. So here's this nice tube. It's kind of weird looking with these different locations, and let's think about which has the most pressure. Pause, rank the pressures. Okie dokie. So last year, I'm going to take what my class thought the pressure rankings were. So last year, the proposed ranking was E is greater than D, which is greater than A equals C, which is greater than B. So then we wondered about B. Like, we don't really know what's going on with B. B has the same height as A and C. But A and C seem to have the atmosphere on top of them too. Well, B just doesn't. So when you have a problem like B, where you don't know what's on top there, if anything at all, then you can't just set up P bottom equals P top plus rho GH, because you're going to have this unknown P top. You're not sure, right? That glass can be pushing down on the water. You could extend these columns up, fill them up with so much water that the glass would shatter. So the reality is, for location B, you have no clue what P top is. The only way that you're capable of solving for location B is to know that it's the same height, depth as A and C. So you have to use this principle called hydrostatic equilibrium to determine that PA equals PB equals PC, because they are all at the same depth. And that is a tool that you will use often. You have still non-moving water. You may use the concept of hydrostatic equilibrium, and that's the only way you can solve about location B, because you just don't know what the container is doing. So then when we reevaluate this, we as a class decided, no, it's actually equals here. Great job, everybody. All right, so we'll move on to try some of these problems, but I'm going to let you look at them all. Try this page by yourself, then go hit up your lab. I will continue this video by solving this page out for you. I'll also solve this page. They get harder as you go. I don't require that you do all of them. Just pick a selective one, so perhaps 3 and 5, for example. But I'll do the whole thing in just a minute. All right, so you tried these, and now we're just looking for a review. So I'm going to start with problem 3. Problem 3, just going to do some P bottom equals P top plus rho GH. So P bottom equals the atmosphere, 1.01 times 10 to the 5th newtons per meter squared, plus the density of seawater, which I got from the front page, times 9.8 times the depth, 4,000. There you go. Bam. Pressure. Titanic. Blah, blah, blah. Barometer. This is a barometer. It's a tube where the pressure up here is 0. So it's completely vacuumed out there. And the bottom parts are exposed to the atmosphere. So this location right here is at P atmosphere. And so depending on the weather, the atmospheric pressure changes and fluctuates, and the column in here will actually change height. So it's a device used to measure if it's going to be stormy and humid or not. Okay, so the pressure at every point in a horizontal location is the same. It's hydrostatic equilibrium. So PD equals PC, but also equals PB. And where's PB? PB is on the bottom and A is on the top. So it asks us using mercury to find how tall a column of mercury corresponds to a normal atmospheric pressure. So what we're going to do is we're going to set up P bottom equals P top plus rho GH. And here we're going to have the P at the bottom is actually PB. The P at the top is going to be the pressure at location A, which is 0. And then our density is going to be the density of mercury. Bam, right? Mercury is dense. So let's take our P bottom, which is atmosphere. So 1.01 times 10 to the 5th equals P top, which is P at location A, 0, plus the density of mercury, 135.95, and then gravity, and then we're going to solve for this H. So I get my mercury column to be a height of about 0.76 meters. Notice I didn't keep quite as many sig figs as they want, right? Stick a 3 in there. Oops. And like, think about how big that is. I mean, it's like this, length of your arm. And that's still a pretty long column of water. So, a column of mercury. Now let's try this again with water. It's going to be a big difference. So we're going to have 1.013 times 10 to the 5th equals P top, still 0. Now I'm going to change this density to only be 1,000 gravity. And H. Solve for H. What? 10.34 meters? No way. Think about your normal house, only 3 meters tall. So it's 3 times as much. That would be very, very useless. Right? For a measuring device. Oh yeah, let me just go look at my barometer, honey. Oh yes, it's can pass me a ladder? Pass me like 3 ladders? Right. Huge column. That's why we use mercury. It's much denser. So here it says if clear weather is associated with high pressure. Clear weather associated with high pressure. Sinking air. How's the barometer used? To indicate weather. So if this pressure increases, then the height of the water column will increase, and then that means that our clear weather is happening. Nice. Okay, let's look at a drinking straw. So when you use a straw, you actually take the atmospheric pressure here, which pushes down in the water, P atmosphere, and then you have to make an atmosphere, you have to suck on the straw, making it something that is less. P. Your mouth has to create like a vacuum. And so we want to know what height we can suck the liquid up if our mouth makes this vacuum that's 98.5% of the atmospheric pressure. So we're just going to go ahead and fill in a little P bottom equals P top plus rho GH. It's kind of how we start all these problems. Figure out what's on the bottom. Well, here it's P atmosphere on the bottom. You don't have to go down here. You can go at any level you want that you know about. So here I'm going to go for P atmosphere equals the P at the top. The P at the top is going to be 0.985 P atmospheres plus the density of whatever we're drinking. If we're just drinking water, we'll put that. And 9.8. And then this height H, this depth below. Notice it doesn't matter the straw's at a diagonal, right? We're only interested in how high we can get it. H. The area part does not affect our pressure. So then we have 1 P atmospheres minus 0.985 P atmospheres. So just to mathematically simplify, you're going to have 0.015 P atmospheres equals 1,000 times 9.8 times H. And we can solve then for our H, 0.154 meters. So 15 centimeters, that's pretty good. Nice job. If the fluid's now a milkshake, what's going to change? So will you be able to suck a milkshake as easily? No, right? You have to create more pressure to get that same height. So if you're just creating that same pressure, but your milkshake is much thicker, we're not going to be able to bring it to that same height. What is the tallest straw you could ever drink from? That's a great question. So if you can make a perfect vacuum where you change this P top to be 0, you actually end up with the barometer problem from above up here. Whoop, choom, and you get a 10.34 meter long straw. Only if you're drinking water. If you're drinking a milkshake, it's going to be shorter. So if we just write that out, basically it's going to look like P atmosphere is on the bottom, and the most pressure at the top you could ever make, or the least, I guess, is 0. Then you're going to have plus rho, and then G, and H, and then you discover it, same setup as before. So 10.34 meter long straw. Now, I haven't ever seen a 10.34 meter long straw, but there's a lot of time right now, so maybe you can make one, okay, and try to drink out of it. Good luck. All right, let's move on to the this weird U-shape tube here, and it's filled mostly with water, but it looks like you put some vegetable oil on the side here. And vegetable oil, we know, has a different density than water. And so we're going to just gently add it on top, and it'll stay on top. So we got our water and our veggie oil here. Water and veggies. So let's rank the pressure, A, B, C, and D. So try it, obviously, before you watch this video. Here's my thought. C and D are on the bottom, so I know they're going to have equal pressure. So I'm going to say C equals D. And I know that they're going to be greater than A and B, but let me just think of how A and B compare. A is under a height of water, while B is under oil. But oil is less dense than water. So there's more oil, but it's less dense. And on A, there's less water, but it's more dense. So maybe that balances out. Maybe there's this principle called hydrostatic equilibrium, where everything at the same depth has the same pressure, because it has to have this equal forces to be balanced. And so we can conclude that A equals B by hydrostatic equilibrium. Cool, let's set it up. So here we have that at this level, PA and PB, we know they're equal. PA equals PB. Let's see what else we know. So this is P atmosphere, P atmosphere. And this is P atmosphere, P atmosphere. So let's write out an equation for PA. So PA equals the atmosphere, which is on top of it, P atmosphere, plus the density of water, rho, G, and H1. Now let's write out an equation for PB. PB, that has the atmosphere on top of it, P atmosphere, P top. But then over here we're going to have oil plus rho, oil, G, H2. And it looks like we know H2. And we know the density of oil as well, and we know the density of water. The only thing we don't know is HI. So if we go ahead and set these two things equal to each other, right, since PB equals PA, what are we going to have? So we're going to have this equal to this. Let's simplify. P atmosphere cancels. Gravity cancels. So we just end up with the density of water, 1,000, times H1 being equal to the density of oil, 920, times 0.05. We can solve for our H1. Nice. So basically it's like density times height equals density times height. That's what it comes down to. Pretty neat, pretty neat. We can solve for H1, of course, and we will get this answer here. Here's challenge problem 7. I leave it to you to challenge yourself. The answer is listed. Good luck.